So this is the perturbed Hamiltonian operator. Okay, where we know the Schrödinger equation using this perturbed Hamiltonian operator cannot be solved. Okay, mathematically, analytically, we cannot solve this. The second order differential equation here cannot be solved. So we want here to introduce an external fields. Okay, in these examples, okay, we introduce the magnetic fields. So once we introduce this, okay, we must include this perturbations in this Hamiltonian operator. So we have here these third perturbations in this perturbed Hamiltonian operator. So basically we have here three perturbations. So now we have determined here the angular momentum here, the total angular momentums. Okay, for these two electrons, the total angular momentum for these two electrons. Okay, where the quantum number, okay, for this total angular momentums, okay, for both total spin and the total orbitals, a good quantum number, okay, where their operator for the total spin and the total orbitals and its components, okay, the components of the total spin and the components of the total orbitals, the operators here, okay, commutes with the Hamiltonian operator, where we can determine the totals here, the magnitudes of these totals vector, orbitals and spin, okay, together with its components of this vector. We can simultaneously determine, okay, measure with energy. And this is the energy. And now we want to, okay, this triplet, what we call this, P, okay, this triplet P from, okay, so we have here this total orbital angular momentum vector and the total spin angular momentum vector. Okay, we can draw this, okay, the vector diagram something like this. Okay, now we want to couple this. Okay, we want to couple these two vectors. To get this total angular momentums vector. The total orbitals angular momentums couples with total spin angular momentum vector to get this total angular momentum vector. Okay. Now let's say this totals J, okay. This total J lies on this z-axis. When this J here lies on this J along this z-axis, of course, all the components of here, this J, will give same energy. Okay. So with the same J value here, you can see. Okay, so we have here the atomic term symbols. Okay, when we couple these two vector, the Russell-Sanders coupling here, okay, we can determine this total angular momentum quantum number, okay, where either L plus S up to here L minus S. Okay, so for different here L and S, so we'll get here the let's say here we have this triplet P with angular momentums, this total orbital okay, total angular momentum here, total orbital angular momentum quantum number is 1. Okay, right here this is S is 1. Okay, S1, this is you 2S plus 1 here. Okay, to get this triplet state. Okay, triplet P state. Okay, now from here, okay, we can get here all possible this J, the total angular momentum here. Okay, 1 plus 1 is 2. The maximum value here for J and the minimum value here is 1. L plus S here minus 1. Okay, and so on. You can proceed here until L minus 1. So we only can get here two values of J. Sorry, not two value, 3. Okay, 1 minus 1 is 0. So here is 2 minus 1. Okay, you get here 1. Okay, so we'll get this with fixed value of, okay, so we'll get here triplet 2, triplet P1 and triplet P0. Okay, we fix value here. Okay, when we put this, okay, vectors, okay, precise here in this z-axis, all the same J value, okay, will give same energy. So we have here 2J degenerate state here having same energy. So for the J2 here, so we'll get here 5 false degenerates energy. So looking back, okay, at this diagram, so we have here 5 degenerate energy here. 1, 2, 3, 4, 5. So this one we have here 1, 2, okay, how many? 2J plus 1, 2J plus 1 is 3. Okay, 2J plus 1 here is only 1. You can count here, the total here, okay, is 5. So we have here 2L plus 1 and okay, 9 degenerate energy. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now this energy splits into different J values, J0, J1, and J2. Okay, now we are going here to apply this magnetic field. When we apply this magnetic field here, okay, the J here, okay, precise here around this z-axis. Let's say this B, the magnetic field vector here, okay, line on this z-axis. So the J here, of course, with 5 different components here of this vector, it will give different effect to these external fields, the magnetic fields. So different value of this component J will give different energy. So this is a 0 H bar. So this is 2 H bar. Okay. We have here H bar. Depending on this B, okay, the orientation of B. So this is minus. Okay, so this slightly split into different energy, okay, which these 5 vectors close to this magnetic field vector, okay, it will give these atoms, okay, is with these components, okay, of J. Let's say this, okay, is more stable than this one. Let's say, okay, this is close to this magnetic fields, okay, vector. So this is less stable than this one. And you can see here, okay, slightly here split into different energy. So the different here is 1, okay, we have number here, and this is, okay, is about less than 0.0 somethings, okay, the unit here compared to this value. So the gap here, okay, is very small compared to this one, and this one compared to this one, okay, is very small, the energy here. And also between these two different electronic, two different J. Here, this is same as J, but different spin multiplicity here. Okay, so this is J, the coulombs, different coulomb. K, sorry. This is 1s, still 1s, 2s, So this is J. So this is different K. Plus K and minus K. Okay, this is plus K, this is minus K. Okay. So spin orbit interaction here. Okay, we can determine here. Okay, the J quantum number here through this scheme, the Russell Saunders scheme here. Okay, so this can be shown. Okay, how this L here, we can relate this L with S to get J, the quantum number. Okay, when the coupling of these two angular momenta, the J quantum number now, okay, is a good quantum number, and the operator here for the J square and the component of the J Z, okay, component also commutes with the Hamiltonian operator. So, in other words, we can determine this simultaneously, the total angular momentum quantum number with energy, this energy. Okay. Now, we want to determine the okay, when we apply these magnetic fields, okay, all different J here, all different MJ here will give different energy. Okay, now we can see here how we remove completely the degeneracy here. Okay, 5 degenerates energy here into different energies with different MJ. Okay, 2, 1, 0, -1, and -2. And this as well for the triplet P1 here split into 3 different energies. And here the non-degenerate here, okay, remain as this same MJ 0. Okay, we only have here only one MJ value. And also you can, okay, figure out for this triplet singlet P1 here, where we can give here 3 different MJ, 3 different energies, okay, with different MJ. Now, okay, we want to determine the quantum number. Okay. We know, okay, so that we can write the atomic term symbols. Okay, so we have here the ground state, the first excited state, okay, when we introduce the magnetic inter-electron repulsion here, so this will split into two different energy, 1s to s. So we have here, so this is triplet P, this is the singlet P, right? So how about this one? What is the atomic term symbols, okay, to write for these electronic configurations? Okay, how we determine this? Okay, and this one you can see, okay, this is triplet S and this is singlet S. Okay. This S0, S10, S the spin multiplicity, the spin quantum number for these two individual electrons. Okay, so this is L0, and using the angular momentum addition rules. Okay. You can get here. Sorry, this is not zero. Sorry. Half. Half plus half is 1. So we'll get this triplet. Half minus half. Okay, we get this singlet. 0, 0, we get this SS. Okay. How about this one? Here we use the angular momentum addition rules. You can use directly this angular momentum addition rules to determine this total L and the total S. Big S and big L. How about this one? Can we use directly the angular momentum addition rule? Can we? Okay. You can see what is the difference here. This is still 2 electrons here occupied in 2 s orbitals. This as well, 2 electrons here occupied in 1 s orbital here. Okay. This is here is 1 here, the quantum number, the principal quantum number here. And this is 2. This is only 1. Okay. We say that when these 2 electrons or more electrons occupied in this here have same set of quantum number here, and S, okay, these electrons, okay, these electrons are called equivalent electrons. This is equivalent electrons. These 2 electrons here are not equivalent electrons because we have at least 1 here, quantum number here, like in this example is N. They are different here. N1 and this is 2. So these 2 electrons, okay, are known as non-equivalent electron. Okay. And this electronic configuration, okay, this orbital is fully occupied. And this electron also, okay, is a closed shell electron. Okay, now we can assign this different 3 different kind of electrons. Okay, the closed shell electron here, the equivalent electron and the non-equivalent electron. So you must identify, okay, this of electrons in use approach, okay, that you need to use this L and S. so that you can get these atomic symbols. Okay, so you must know this one. Okay, so the closed shells electrons, okay, is always the equivalent electron. Like this, 2p6 is the closed shells, and this is the closed shell orbital. 3d10 is the closed shells. These 10 electrons are the closed shells electron. So now, okay, now we want to begin with closed shells. So for all closed shells electrons, you only can get this singlet S. Examples. You can use directly this angular momentum addition rules. This, you can simply use this rule for equivalent. And we know that closed shells electrons, okay, is always the equivalent electron. And we have, okay, this one as electron, two electronic configurations here, okay, in these examples. And also the P6 and D10. Okay, this also the equivalent electron. Okay, for the equivalent electron, okay, in this case the closed shell electrons, we must get out from this table. For the this 1s, 2s, you can get the 0, 0, this, okay, the examples. This table is for the 1s2. For the 1s2s, you can get here the same set quantum number. Because we have here at least one here, okay? In examples, the quantum number here, at least one here, different. 1 and 2. So the M L here. So this is for the MLs, this is for the MS. This is the component of individual quantum number for electron 1. This is electron 2. These are the components. Sorry, not component. Component of spin. This is component of orbital. This is component of spin. Okay, so you must know how to differentiate this as half and L0. S is only positive value. The MS here could be positive half and negative half. So we have another here, positive half and positive half. this still 0, and you can have here positive half and negative half. Okay, for this one. So the M here is 0, the total M here, okay, the sum of these two values, 0, 0. The MS, okay, we know this one. So this is the M, right? The MS. Okay, you have seen this in our last video. The negative half is 0, positive, positive, 1, positive and negative is 0. So this one, MS here, okay, sorry, this is not 0, this is 1, negative 1, okay. This is negative 1, MS. Negative half, negative half, negative 1. So the minimum value here is negative 1, the maximum value here is 1. Okay, in between here, 1 and negative 1 is 2. So this is L1. So the L1 is the P. The spin of all 0 here. This will give S 0. This is triplet P. The triplet P here is the one S to S. Okay, and at the same time also you can get here singlet P. Singlet P also is one of the atomic term symbol for this one S to S. So we have two term symbols for one S to S. Okay, how about this one? What we can conclude here, we can use directly the angular momentum addition rules, and the angular momentum addition rules, okay, like what we have done here, this one, okay, L10, L20, S1 half, S2 half, you can use angular momentum addition rules to get all possible here, the term symbols here, okay, triplet S and singlet S. Okay, sorry. This is not P. Okay. I meant tulis saja. Okay. This is okay. Singlet, triplet. Okay. This is triplet. This is M. This is L. Okay. Please correct me. This is L. This is S. Okay. So you get here triplet S. Okay. So this is singlet. Okay. So again, MS negative to 1, so S1. So triplet S. So here is L0, so this is S. S. So now the angular mathematician rules, we can get here all possible term symbols for this. Okay. Yes. For the electrons, okay, closed shell electron as well, we only can get okay, because we cannot have a set of quantum number. Okay, due to the Pauli anti-symmetric principles, okay, we have another Pauli exclusion principles. Okay, there is no same set of identical particles like here these electrons, same set of quantum number. So we have here this same N, we cannot have this same M, L, here MS, N. Okay. So remove this one. And this cannot. And this one, okay, they are same. Because these two electrons distinguish these two electrons. Either this plug is half here or here. Okay, sorry. Negative half here or positive half here. Negative half or positive half, okay? They are the same. We only have here 2 rows. Okay, we eliminate here the other 3 rows. For the ones to for the closed for the equivalent electron and the closed shell here, the closed for the equivalent electron, the third symbol here you can see we have this 2 term symbol here reduced to only one S. So for any here, what we can conclude here for the non-equivalent electron here, okay, when we write here equivalent electron with same orbitals, like in this example S orbital of this equivalent electron here, the number of atomic term symbol here reduce, okay, to only from 2 to 1. Okay, so this number of atomic term symbol for equivalent electrons, okay, a subset of this number of non-equivalent electron. Okay, so from 2 to 1. Okay, how about another here for the P6? Okay. Okay, you can see this fully occupied and 3 sub-shells orbital here. 0 with quantum number here. Okay. And the same N, let's say this is 2, same N. Okay. So to have all these different set of quantum number, okay, we only can put like this. Okay. So the M1 is here -1. M2, if M2 is -1, so at least 1 is different. Where is MS1? MS2. This is MS1. So the MS2 is -half here, MS1 here is +half. Okay, so the M here, okay, what you can get here is negative 1, right? 0 plus 0, this one. Positive 1, positive 1. So this is 0. 0 is S. This as well, for the spin. For the spin here is positive half, negative half, positive half, negative half, positive half, negative half. Okay, this will give 0. So you have here only singlet state. Singlet S state. Okay, if you construct this table, you only can get one row here. Different combination of this M. M1, M2, M3, N, okay, till M6. M1S, M2S, okay, up to M6S, okay, for this quantum number. So this is the total one. So for the closed shells orbitals, okay, you can get this singlet S. Okay, for the non-equivalent electron, okay, like this one S2P, you can use this angular momentum addition rules. Okay, this angular momentum addition rules. So this what we get here. Okay, this is how we describe this triplet P with quantum number. This one triplet P as this is the P. This is singlet P. Okay. Okay. This in these examples we use one S 2P. Okay. Right. One S is 2P. You also can use an approach. Okay, using that tables. You can tabulate here all the combination of quantum number. Okay, all possible quantum number. Okay, you get these 12 rules of different combination of quantum. Okay, for this 1s P here, okay, could be here this negative 1, positive 1, or 0. Okay, M1 here, okay, all these 0, 0, 0, all 0. MS here, only two values, positive half or negative half. So this is the total one. And then you can identify, okay, each of these row. For examples, for the L1 here, and S1 here. This could be this value, okay? Oh, not this one, this is J, sorry. This one. This will give L1. Okay. Can this be L1? Okay, cannot, because we want to look here for this S1. Okay, in these examples, for the S1, we have S 1, 0, -1. Okay, so we cannot have these combinations. If 1, they must be -1 and 0. If the maximum value is 1, the minimum is -1. So we cannot have this one. Okay, so we cannot select this row. Okay, if you want to choose this one, you must have this one and this one. Cannot. Yes, this is M. -1, +1 and 0. So we can use this one, L1. At the same time, the MS here, if we choose this +1, we must have this one. Okay, between is 0, so this is S1. So now we can eliminate this row. Let's say this row. To get this. So how about J? We know the rest from the rest under coupling, L plus S till L minus S, so you get 0, 1, 2. Okay? You also can prove from here. This is MJ0, MJ plus 1, MJ minus 1. So this one, for the MJ, so this is 1. MJ, J1. Okay? So the MJ1 here, sorry, this is MS. J. Zero, +1 and -1. Okay. Cannot. Okay, cannot, sorry. Okay, because we only can get here this 1J, this J1, J +1. Okay, we want to have here this J with 3 J values, 0, +1 and +2. Okay, so now we want to have here this one we can include this one, this J negative 1 with same M here. And positive 1 here, positive 1 here with 0 and 0 here with positive 1. So all this zero, negative, positive 1, negative. Sorry. Bit messy here. We have here J1s. How about J0? This is J1 negative 1. Positive 1. This is positive 1. Okay. It's only 1, 0. Okay. This we have here MJ negative 1, 0, and 1. So this is the MJ negative 2, negative 1, 0, 1, 2. And this is MJ 0. Only one value of 0. Okay. I forgot this one. This is suppose. How many value here? Zero, 1, 2. Okay. This is 0. Okay. So this is 1, negative 1, positive 1, and 0. So we get here this L1. So, and the J as well here, negative 1, positive 1, and 0. We get here the J1 here. Okay. And also we can have here 0. Okay. This one. For L0, J0. L0, J0 cannot. This is, no, cannot this one. Cannot this one. J0, L1, S1. L1 S1. So how many zero here? This we have the 30 ms 30. 1, 2, 3. MJ. These combinations 0, 1, 2, 3. 1, 2, 3 is here is 0. Is it correct, this one? Can you help me? How to find this one? L1, S1, and then MJ0 here. Okay? To get this L0. Ada pening kepala. Okay? So this is J2. This is J1. Yeah, so this is L1. Negative 1, 1, 0 is 1, correct? This is the MS, positive 1, 0, negative 1. So MSS is 1. So the J1 here is 0, positive 1, negative 1. So J is 1. Okay, we have got this one, L1, S1, so J is 1. We know J is from 0 to 2, okay, because of this one, the L. So how about this one, the L0, the J0? We must find combination of this M. Negative 1, positive 1, and 0. Okay, this one to get this L1. So S and J together. Okay, so we can choose this one, positive. This is okay. Let's say we want to choose this one. Okay, for the J2. Let's say we want to choose for J2. So this one, okay, I use different color. Okay, I will use this different color. Okay, so this one for the L, the M here, ML here is 1, still 1. With the MJ, the maximum and the minimum value, okay, this one. So we have here negative, okay. So this is positive. So we have another one here, negative and positive. This one, negative one, and this positive one. Okay, this with this one combination, and zero. Zero value here. We can choose this spin. Okay, spin must be one also. Okay, so this spin, the minimum here is negative one, the maximum is positive one. Okay, in between is zero. So we can also select this one for J between is negative 2 and positive 2, 0. So all this set, okay, L1, S1, J2. Okay, I found here uh, for the positive, and negative one. Oh, there's something wrong here in this table. Okay, only one here. This is L1, L1, and then 0. We must have here another combinations of L. Oh, 0. So this is 0, negative. So we cannot use this one. L here must have this, sorry. ML0. Okay. So zero, negative one here, 1. Negative one, positive one, and 0. Negative. Only last value here, okay? Only last value here. For this one, 0 here, the J 0. So we must have this all 0, this 0. Okay, all 0. We must have all 0 here. Okay, this one, -1 and -1. Okay, this one, 0. So oh, this cannot. J must be 0 here. So MJ must be 0. This cannot be. This cannot be. So this one, okay, we can have this one. Okay. +1, 0, we must have here -1. We must have here -1. +1, 0, we must have here -1. This is okay, 0 and 0. MJ. The only one here, okay, we can use this one. This value. So the MS also here, -1, 0, this +1. Okay. Let me correct this first. This is MJ 0, 0, 0, 0. The J will be 0. The MS +1, -1, 0. So we get here the S is 1. L, -1 to +1 here. Okay, here in between here is 0. So we'll get here L1. Okay. How about for this one? The L1 here. Okay. So we can have this one. This one. Okay. Yeah, we can have this one. -1. MS. Let's say this one. So we have here 0. We must have here -1 and -1. Zero. So if we have here 0, we must have the MS here, positive and -1. So let's say we choose this one. Sorry, do you have class after this? Okay, I'm struggling, okay.
Doctor,
Yep.
maybe you can clarify first and then you get back to us next week.
Okay, next week. Okay. Okay, I'm having problem now to eliminate one by one this row. Okay. Maybe we can continue next week. Okay, I will try to solve these problems. Okay. Actually, everything is in the, okay. I can refer this entry, first, and so on. Okay. I'm trying here to solve it without looking at this row. Okay, eliminate the first, second here. So from here, you can get this one. Okay, this combination. Okay, and this state. Okay, we can stop. Suppose I want to finish this lecture. Want to finish this lecture. Okay. once we have finished this, okay, this topic, to finish this until the end. So we will continue next week. Okay, I will try to solve this problem and try to explain how we can use these tables. Okay. To some for the equivalent electrons. Okay, for the for the non-equivalent electron, you can use this angular momentum induction rules instead of using this. Okay, these tables. Okay. It's actually easier to use the angular rules to find the symbols. Okay, rather than these tables. For the equivalent electrons, for the closed shells or equivalent electrons, this is non-equivalent electrons. For the equivalent electron,